Good afternoon, this is Schweitzer, and we're going to be running a start of our series of videos on gases. Our gases follow the same pattern kind of that our liquids and solids did. Why is a gas a gas? We're looking at some both internal factors and some external factors. Let's start this off here. The next few slides will take notes on this page here. And we're going to kind of introduce the idea of what's an ideal gas and what is a non-ideal gas. Okay? So, with that being said, what's an ideal gas? Okay, so the idea of an ideal gas is that particles are starting to, well, they're separated by quite a long ways. And we know that with Coulomb's law, for example, the force between two particles is the inherent charge on the particles. Positive, negative, and divided by the distance squared. Well, if that distance gets really large, then this force really drops off. And the idea here is that there are no interactions between particles. So therefore, when you compare particles, basically this is just a particle X, this is just particle Y, and it doesn't matter what the particles are. Okay. So the identity of the particles do not matter. All particles act the same because there's no interactions, there's no attractions, there's no repulsions, there's no nothing. They don't know anything. Sometimes I make the idea of like when you go jumping into one of those things with all the balls in it. Okay? The color of the ball doesn't matter. Right? Here, the identity of the particle does not matter. We want to understand why. They're so far apart, the attractions are so weak, and they're also traveling extremely fast. That's two things. One, they're very fast, and they're very far apart, so therefore the attractions are zilch. Now, sometimes I sort of make the analogy of ideal gases kind of like unicorns, okay? Unicorns, my daughter, for whatever reason, she loves unicorns, okay? I think she thinks that they actually kind of exist. But, that being said, they don't exist. Okay, sort of burst your bubble. Okay, there's no unicorns. So do ideal gases really exist? And the answer is kind of no. They don't really exist. Particles, even on the smallest levels, are slightly attracting and repelling. There's still some force there, some more than others. So ideal gases is kind of a generalization. We can't tell what these small attractions are, so we just ignore them. We just estimate. Engineers do this all the time. You're never going to know exactly what something's going to do. You're never going to know the exact, weight a bridge can hold. So they estimate, and they say, okay, with these variables, we should be able to have a certain window of weights of cars, how many trucks we got on here, the wind loads, and they just estimate within ranges of reasonability. And that's what we're doing with an ideal gas. Now, there are some factors that can cause gases to act more like ideal gases, and some that could be not so ideal. If it's ideal, non-ideal, then they're definitely attracting a pretty good rate. Sometimes I make the analogy as if you're driving down 41 and all of a sudden you pass your grandma's. Grandma's going this way and you're on the other side going that way, and there's almost no interaction between you two. So with that being said, why don't you wave to grandma? Because you don't know she's there. But if you're walking down the sidewalk in front of the high school and you're walking this way and grandma's walking the other way and you don't stop and say hi to grandma, well, that just makes you kind of a rough grandkid, or grandma's going to slap you, all right? So you're right close, you're going slow. So the two factors are distance and speed. Again, maybe grandma's, there are some factors that can really make these things more likely to attract. One is if there are inherent attractions between each other. If the inherent attractions are weak to begin with, well then they're more likely to be ideal. If their attractions are strong, now again, we've talked about these inherent attractions. They're the intermolecular forces. If those are strong, it's likely not to be as ideal as you might think. Okay? So we might compare particles
just in a sense of who's more likely to be like this unicorn, or more likely to be, non-ideal. All right, so again, ideal gases. Here we go. How do gases become more ideal? As I've mentioned, little to no attraction between particles because they're traveling very fast and they're very far apart. So if these conditions fail or become compromised, then we can be moving more towards non-ideal. All right. How do we get particles to start interacting? Well, okay, we want to get these two conditions just to reverse. So I want to increase my pressure. That means my particles, which were very far apart, okay, and very rarely running into each other, are now, let's say we squish them into half the volume, or even less, a tenth of the volume. Now they're constantly running into each other because they're so much closer, creating more pressure.
Increasing the pressure drives something to be more non-ideal. Lowering my temperature slows them down. So the amount of time they're next to each other is longer, giving them more opportunities to interact. All right, sample question. Which of the following conditions was most likely to display a non-ideal character? Okay, so we're looking for, take a moment, we just talked about what we're looking for. We're looking for lower temperatures and higher pressures. Okay, all right. Which of the following substances is most likely to violate the ideal gas law? So which most is likely not to be ideal? I've drawn some of these out here, just kind of give some hints as far as shapes are concerned. We're looking for who inherently has the most intermolecular forces. I'd be looking for things like hydrogen bonding or a dipole-dipole. Those are some consistently large attractions. I might also be looking for something that is symmetrical. If it's symmetrical, then I have a dipole moment of 0. Okay? So O2, dipole moment of 0. Benzene, very symmetrical. Dipole moment, 0. Carbon dioxide, dipole moment, 0. The only one that got this bent shape with 3 electron domains, this one's got a dipole moment. So it's got some amount of dipole attraction. So this one is one that's likely, because it inherently has force of attraction, charge of positive, charge of negative, divided by the distance squared. For a given distance, it has more attractions between the particles. So more likely to maybe deviate from a ideal gas situation. All right, we'll stop our video here. We're going to end this video on internal attractions. Basically, our internal attractions are that there are none. Okay, for the most part. All the stuff that we'll be doing are just for ideal gases. Again, to review, if we're doing all ideal gases, then the one thing that seems like should really matter that doesn't is the identity or the type of gas you're dealing with. The type of gas, okay, does not matter. Period. Okay? Does not matter. And that seems weird. If I have a balloon, let's say, of oxygen gas, or a balloon, let's say, of helium gas, they're the same size, we might not know, looking at that one's helium, one's oxygen. Just don't know. Alright. Thank you very much. See you next slide.